Philip, can you hear me? Okay, I think both the students are about to join in. Uh, right. Is everyone able to hear me?
I can hear you. Who is?
Right, right. Both of them have actually joined the meeting. I think they're on mute right now, George and Philip. Uh,
Yeah, I can hear you too.
okay, okay, fine. So we'll begin. Today, the topic of the discussion is going to be sequences. And okay, and we are going to discuss some problems on sequences, and through the problems, we'll discover some techniques that are important for you for Olympiad problems. So let's begin with the first one. This is the first question. Sequence AN satisfies that for any non-negative integers m and n, where m is greater than equal to n, the condition a of m plus n plus a of m minus n is equal to half of a of 2m plus a of 2n. It is also given that a of 1 is 1. You have to find the general formula for the sequence. Find the general formula for the sequence. So this is an easy one that we'll start off with. Both of you can try it out and see if you're able to find the general formula here. The first step in most of questions like these is usually to try to figure out a pattern in the first few values of the sequence. Let me know if anybody is making any progress. Is anybody getting any lower values of the sequence? If you try to put m is equal to n in the general relation here, what do we get? This relation should be obvious to everyone, which implies that A2m plus A0 is equal to A2m, which implies A0 is equal to 0. I hope everyone is following what I'm saying. We have gotten the values of A0 and A1, and you can try and find out other values as well. George, are you getting something? Let me know if there is a problem, if you're stuck somewhere, we can discuss it. If you don't say anything, I will not know if you have a problem. Philip, are you able to hear or unmute yourself now? Is there still a problem? Yeah, you are on not on mute anymore.
You hear me?
Yeah, I can hear you. Are you making any progress in this question?
I found that for some values, I think it will be like n equals n squared.
Correct. So you found some values, right? We have seen the first couple of values, right?
Yes,
And you can see this relation also, A4 is equal to 4 times A2 and stuff like that, right?
yes. I found that 4am equals 8 to m.
Okay, how did you get that? A2M is equal to 4AM,
I put n equals 0.
right? So you get
So
A2M twice, right?
yes,
Is equal to half of A2.
no
Okay.
am, not 8.
You are getting N is equal to 0. Oh, okay. You're getting AM, not A, right? If you
Yes,
put N is equal to 0, you get this plus 0. So you get A2M is 4 times AM, right?
yes,
Which means that if we can find out A2, then A4 will be 4 times A2 and stuff like that, right?
yes,
And we already know A1, so we can find A2 from this relation, right?
yes,
A2 will be 4 times A1, and A1 is 1, so A2 is 4. So basically, the beginning set of values we can guess, and now we can say that probably an is equal to n square, but this is not a proof. You need to prove this also, right? This is a conjecture. We are making a guess that it looks like this pattern should be true. So how do we prove this? The next step is basically making a proof for this. So you should use induction to prove it. So you can use the induction with step size 2 and assume that am minus 1 is m minus 1 whole square. and AM is n squared. This is our assumption in the induction step. We already know base case is true because A0 is 0 and A1 is 1 and A2 is 4. So now the next step would be to prove AM plus 1 is m plus 1 whole square, right? I hope everybody is understanding what I'm saying.
Yes.
So let me know if you're done with this proof. You have to use the condition given to prove this. This step is not very difficult if you use the condition in the given in the question. We can say that AM plus n plus AM minus n is equal to half of A2m plus A2n. And here you can put n is equal to 1. You will get AM plus 1 plus AM minus 1 is equal to half of A2m plus A2. And we already know AM minus 1 and A2m because A2m was 4 times AM. And we know AM and AM minus 1 from our induction hypothesis. You can figure out what AM plus 1 should be now, right? This is what is coming, and you get 2m squared minus m minus 1 whole square plus 2. And this becomes m squared plus 2m plus 1, which is m plus 1 whole square. Which basically means that am plus 1 is also fitting the same pattern, and that finishes our induction. I hope that is clear.
Yes.
Okay, so that tells us that in general, an is n squared. And that it finishes our proof for this problem. That was an easy one to start off with. Let's look at this particular question. Let n be a given positive integer. The sequence A0, A1, AN satisfies A0 is equal to half, AK is equal to AK minus 1 plus AK minus 1 square divided by n, where k goes from 1 to n. So these are the conditions satisfied by the sequence, and we have to prove that 1 minus 1 by n is less than an is less than 1. We have to establish this inequality for the last term of the sequence, and these are the relations that is being satisfied. Some basic information that you can figure out from this relation is that n was a positive integer, so the second term here is always positive, ak minus 1 whole square by n. So that means that tells us that ak minus 1 is less than ak, right? And because a0 is half, the higher term a1 is bigger than a0 and a2 is bigger than a1. That is true. Therefore, we can say that all the terms are positive. Because you start off with half, so every term is going to be bigger than after that, right? I hope you follow what I'm saying right now.
Yes.
Okay, so now you have to think of this relation and maybe think of trying to simplify this relation in a certain way so that you can work with it in a better manner. Just think about that condition that is given. one idea that you can use here is try to simplify it like this. Take a common denominator, write it like this. And at this step, you can take factors on top, right? And it would be easier if you work with the reciprocals at this step. I hope you understand what I'm trying to say. You can make it like this. 1 by AK is equal to n by AK minus 1 times AK minus 1 plus n. After this step, I'm sure you can figure out what is the next thing to do here. We have basically simplified the relation and made it look like this. So think about it and what should we do next here? Is anybody getting any idea what to do after this? Think of partial fractions or the method of telescoping series. What you can do is split this term into two separate terms. The numerator can be written as AK minus 1 plus n minus AK minus 1. And the whole thing is divided by AK minus 1 times AK minus 1 plus n. So that clearly becomes 1 over AK minus 1. 1 over AK minus 1 minus 1 over AK minus 1 plus n. That is equal to 1 over AK. Is everybody understanding what I have done so far?
Yes.
Right. So that is useful to us because now I can use the concept of telescoping series and get a few results. What I will do is I will take this term on one side and I'll write it like this. 1 by AK minus 1 plus n is equal to 1 over AK minus 1 minus 1 over AK. And Now you can sum it up because you notice that these terms are different by only one subscript. So if you sum up k from 1 to n, you will start getting some nice results now. So what I want to do here is sum over k from 1 to n on both sides. So this side, it is a nice telescoping series. You get 1 by a0 minus 1 by a1 plus 1 by a1 minus 1 by a2 and so on till 1 by an minus 1 minus 1 by an. And basically, every term in the middle here cancels off and you end up with 1 by a0 minus 1 by an. And since a0 was half, you get a 2 minus 1 by an. I hope everyone has understood that.
Yes.
Right. So basically, so far what we have achieved is by reworking the condition given in the problem, we have rearranged it in such a way that we were able to write it like this. And then we took a summation over the subscript k and we have gotten this. Left hand side is this ak minus 1 plus n. It is coming equal to right hand side. I've done the summation came as 2 minus 1 over n. Now think of what you need to prove and try it out. See if you can prove it. What we needed to prove was this: 1 by 1 minus n is less than an is less than 1. Wait, I have made a mistake here. This was 2 minus 1 by an, not n. If you remember, the summation was 1 by a0 minus 1 by a1 plus 1 by a1 minus 1 by a2 and so on. So I made a mistake and I wrote, instead of an, I wrote as n. So after doing the summation, it was this, right? So it should be 2 minus 1 by an here. I hope you understand. I was making a mistake here when I was writing it as n. The whole problem is still not done, but we are very close now. Once we get till here, you can easily solve the rest. You have 3-4 minutes, guys, to try to figure out this last step. I will tell you the solution if you can't get it in the next 3-4 minutes. Okay. So just try it out. See if you can prove it. Any progress, guys? Okay. So the left-hand side here, you can always say that each term 1 by ak minus 1 plus n is clearly less than 1 by n, right? That should be clear because ak minus 1 is positive. So when you add up, k goes from 1 to n, this thing, that will be less than summation k goes from 1 to n of 1 over n, right? What is the value of this sum? Notice that the summation is over k, but the quantity inside the sum is not having k, right? So this is just n times 1 over n plus 1 over n plus 1 over n, n times. So this is equal to 1, right?
Yes.
So therefore, we have gotten that this summation is less than 1. And that basically means that 2 minus 1 by an is less than 1, which basically gives us 1 is less than 1 over an, and which means that an is less than 1. So we have proved the second part of it now. This part is done. How did it happen? It happened by changing this term of the summation and getting an inequality on it. 1 by ak minus 1 plus n is less than 1 by n from there. So we have proved one part of it now. We have to still prove the other half. So for that, we do a slightly different condition here. What we will do is we have already seen in the beginning of the problem that every ak was bigger than ak minus 1. The series was increasing in that sense. So we had this condition, 0 is less than a0 less than a1 and so on, less than an, and now we also know an is less than 1. So this is known to us. Therefore, what we can say is this summation k goes from 1 to n, 1 by ak minus 1 plus n will be greater than if I replace ak minus 1 with 1, right? Ak minus 1 is clearly less than 1. So I have replaced that with 1. So I get a different inequality now, right? I hope this step is clear to everyone.
Yes.
So now this summation is simple. This is n times this. So it is coming out to n by n plus 1. And now we will say that I will replace this side with 2 minus 1 by an is greater than n by n plus 1. And now it's just a matter of a little bit of algebra. You will get 2 minus n by n plus 1 is greater than 1 by an. You get 2n plus 2 minus n. So you get n plus 2 by n plus 1 is greater than 1 by an. So taking reciprocals, an, if you take a reciprocal here, you'll get n plus 1 by n plus 2 is less than this, which means an is greater than 1 minus 1 by n plus 2. Right? If an is greater than this quantity, automatically an is greater than 1 minus 1 by n. Because 1 minus 1 by n is smaller than 1 minus 1 by n plus 2. Do you understand what I'm doing, what I'm saying right now?
Yes.
What I'm saying is I have gotten 1 minus 1 by n plus 2 here, and that is a bigger number than 1 minus 1 by n, right? So if this inequality is true, this inequality is also true. An is greater than 1 minus 1 by n. The trick in this problem was converting the relationship by simplifying it and taking reciprocals and then splitting the fractions and using the concept of telescoping series. Only if we did that would we have gotten to this stage. And after that, the inequality is not so hard to prove. But that technique must be known to you. You should be familiar with steps like that, taking reciprocals, splitting the fraction into two parts, those kinds of ideas. I hope you have understood the problem completely. Okay. We'll go to the third question. This problem says, for n belongs to natural numbers, let an be equal to n by n minus 1 to the power 4 by 3 plus n to the power 4 by 3 plus n plus 1 to the power 4 by 3. What we have to prove is prove that A1 plus A2 plus A999 is less than 50. So the sum of the first 999 terms of this sequence will be less than 50. They have given us the whole form of the sequence. So actually you can calculate A1, A2 and all, but that will not be very easy to do. Like you cannot make much progress by just calculating it. So you have to think of how to simplify this general expression and get some inequalities there. Notice that since the final inequality that we want to prove is sum of ANs is less than something, less than 550, then it would be nice if we can get an inequality for a general AN is less than something, right? If we can get an inequality like this, then we can add all the ANs, right? Are you following what I'm saying right now?
Yes.
So our target here should be, can I get an inequality like this? AN is less than something. Basically, I want to enlarge my term here. Right? This is less than something bigger. And if I can do that, then maybe I can proceed with the question. So this technique is called, sometimes called lessening or enlarging the terms before we prove an inequality. This is applicable in many problems in inequalities. You take the given condition and try to make it lesser than something or larger than something, and then think about the question. So I'll give you a hint for what you can try here. We have AN is n by n minus 1 to the power 4 by 3 plus n to the power 4 by 3 plus n plus 1 to the power 4 by 3. I would say that we can try and take, this is a very horrible looking term. These are bad terms. So what we can do is make it slightly simpler by thinking of x as n minus 1 to the power 2 by 3 and y as n plus 1 to the power 2 by 3. Right? Then this starts looking like x square. There is a middle term plus y square, right? the denominator, right? What is the product of these two? Xy is equal to n square minus 1 to the power 2 by 3, right? If you think about this, this is clearly going to be lesser than n square to the power 2 by 3, right?
Yes.
So notice that n square to the power 2 by 3 is n power 4 by 3, no? Are you seeing that you are getting xy is less than n power 4 by 3?
Yes.
Great. So now, if I have this expression here, n minus 1 power 4 by 3 plus n power 4 by 3 plus n plus 1 power 4 by 3, I can say that n power 4 by 3 is bigger than xy. So I can easily say that this term is bigger than x square plus xy plus y square, right? The first two terms are exactly equal to x square and y square, but this is bigger than xy, right? Is everyone understanding what I have done so far?
Yes.
So notice that because we have an inequality with the denominator, we can easily say that n by n minus 1 power 4 by 3 plus n power 4 by 3 plus n plus 1 power 4 by 3 will be, the denominator left hand side is bigger than this. So this will be clearly, if you replace it with x square plus xy, it will be less than n by this, right? Correct?
Yes.
So now, aren't you seeing that we are getting an is less than n by x square plus xy plus y square? We are getting an inequality on an, no?
Yes.
So that was the idea. So now an is less than, we are getting an is less than n by x square plus xy plus y square, where we know what x is. X is n minus 1 power 2 by 3 and y is n plus 1 power 2 by 3. So can we make it a little better here, simplify this a little bit? What can we do to simplify this a little bit? Think of some good way to simplify it. You must be aware of the algebraic identities for sum and difference of cubes, right?
We can do times y minus x.
Correct. We can do x cube minus y cube or whatever. X minus y or y minus x. Doesn't matter, right? We should do y minus x because y is bigger, right? Correct?
Yes.
That will make it n times y minus x by y cube minus x cube, right?
Yes.
Okay, great. So now think about it. Y cube and x cube are easy to figure out. No, y cube is simple. Y cube is n plus 1 square and x cube is n minus 1 square, right? Right, no?
Yes.
So y cube minus x cube is simple. That is equal to 4n, right?
Yes.
So this becomes n times y minus x divided by 4n. And basically we have gotten an is less than, n gets cancelled, 1 by 4 y minus x. Correct?
Yes.
Which is much better than what we started out with. It is much better than when we had just this, right? We have now an is less than 1 by 4. We can even write y and x now and write it as n plus 1 power 2 by 3 minus n minus 1 power 2 by 3. We have got this inequality, and now we can just try to add the terms to find out a1 to a199, a999. Because there will be a pattern and it will also be telescoping series sort of situation. You will get something like this: a1 plus a2 plus a999 is less than 1 by 4 summation of n goes from 1 to 999, and inside you have n plus 1 power 2 by 3 minus n minus 1 power 2 by 3, right?
Yes.
Okay, so think about this. What is this summation going to be? Let's write a few terms. You will get the pattern. When you put n is 1, it is starting from 2 power 2 by 3 minus 0 plus, it will be, next term would be 3 power 2 by 3 minus 2 power 2 by 3 and so on. And the last term would be 1000 power 2 by 3 minus, it would be 999 minus 1. So 998 power 2 by 3, right?
Yes, but it's not 3 to 2 by 3 minus 1 to 2 by 3.
Oh, right. This was
Yes.
1, right? Yeah.
Yes.
This was 1. The difference is 2 always between this and this, right? So what we are getting, what would have been the next term? It would have been, if I put n is 3, it would be 4 power 2 by 3 minus 2 power 2 by 3. And we can see here that the second last term would have been 999 power 2 by 3 minus 997 power 2 by 3, right? Correct, no?
Yes.
So notice that this term got cancelled here. This 3 term would also get cancelled with the 5 one, right? The one after this, right?
Yes.
So what will be left? The first 2 terms of the last couple of factors will not get cancelled. The remaining ones will get cancelled, no?
Yes.
I hope you are understanding what I'm saying. I think what will be left is 1000 power 2 by 3 plus 999 power 2 by 3 and these 2 terms minus these 2 terms, right? Are you understanding what I'm saying?
Yes.
So we are getting this sum, the required sum is less than this. Now, okay, so this is clearly going to be 10 power 3, so it is 100. So we are already getting 100 plus 999 power 2 by 3 minus 1, 1 by 4. This is what we are getting. But we can say that 999 power 2 by 3 minus 1 will be less than 100, right? Or 1000 power 2 by 3, right? This thing. Basically, I'm
Yes.
saying I can replace this whole thing and say that it is less than 1000 power 2 by 3. Which will mean that our overall sum is less than 1 by 4 and twice of 1000 power 2 by 3. Right?
Yes.
So this becomes 100 and 200 by 4, and we are able to prove that S is less than 50. So the last part of the problem is not very difficult. The main idea in the problem was what? The main idea was that horrible expression that we had in the beginning. How do we think about simplifying this? 4 by 3, 4 by 3 plus n minus 1 power 4 by 3. We had this expression. And how did we figure out sum which was A1 to A2 till A99? We needed to prove that this is less than 50. So our target was to get an inequality like this. An is less than something. But what was the approach we took? We thought of this as x and y. And we saw that it was becoming x square, y square. And if you write it as xy is bigger than this, right? So we were able to say an is less than this. Xy was not equal to n power 4 by 3. Actually, xy was lesser than n power 4 by 3, right?
Yes.
Do you understand what we did, how we came to the conclusion? Like once we got to an inequality like this, the problem was easy after that because we can take advantage of x minus y by x minus y and convert it to a telescoping series. The main idea is how to think of starting the question. What do I do to begin to solve the problem? If you cannot take the substitutions x and y here, it is very difficult to make any progress. Are you understanding, everyone?
Yes.
Okay. Fine. The next problem that I have is slightly different from what we have seen so far. This question says this. A finite sequence A0, A1, AN is called K-balanced. Is called K-balanced if A0 plus AK plus A2K and so on is equal to A1 plus AK plus 1 plus A2K plus 1 and so on is also equal to A2 plus AK plus 2 plus A2K plus 2, and such properties, such summations are always happening till AK minus 1 plus A2K minus 1 plus A3K minus 1 and so on. If these equalities are true for this finite sequence, we call that sequence K-balanced. Do you understand the pattern here, what we are saying? The first term and the kth term and the 2kth term, the sum of all such terms is same as the second term and k plus 1th term and 2k plus 1th term and so on, right? I hope you understand the structure of the sequence right now. What is a k-balanced sequence?
Yes.
Okay, so the question is saying that it is given that A0, A1 till A49, this sequence is K-balanced for K equal to 3, 5, 7, 11, 13, and 17. So a lot of information has been given. We have a sequence of 50 terms, and that sequence is k balanced for all of these values. K is these prime numbers, right? What we have to do is prove that A0 is equal to A1 is equal to all of them till A49 are all equal to 0. So this is a slightly difficult problem, slightly strange also. But you have to think about how you would even begin to prove a question like this. The given sequence of 50 terms is k balanced. Basically, it is 3 balanced, 5 balanced, 7 balanced, and so on till 17. 3 balanced would mean A0 plus A3 plus A6 is equal to A1 plus A4 plus A7 is equal to A2 plus A5 and so on. That is the meaning of being 3 balanced. Similarly, you can write down what 5 balanced means and so on. So, in order to think about how to do this problem, you should take advantage of theory of polynomials. Like, we can make, you should know that any sequence, if you have A0, A1, A2 till AN, you can make a generating function or a polynomial out of it, right? For example, if my sequence is A0, A1, AN, I can make a polynomial f of x is equal to A0 plus A1x plus A2x squared. This is known as the generating polynomial for that sequence. This is my polynomial. Obviously, this polynomial has degree n, and the terms of the sequence are coefficients of this polynomial. Now, here, our sequence was up to 49 terms here. So, the polynomial for us would be A0, A1 till A49 x power 49. A0, A1x plus A2x squared till A49 x power 49. This is our polynomial here. And why do you think I'm trying to tell you about polynomials right now, even though it looks like a sequence problem? Because we know some theory of polynomials, right? You know some things about roots of polynomials and stuff, right?
Yes.
Here, what you have to prove is that the terms of the sequence are all 0. That is going to be very difficult to prove if you don't use any extra theory. If you don't think of it as polynomials, you don't even know how to start the problem. You will have so many equations, right? You cannot keep manipulating equations, right? The fact that the sequence is k balanced for so many different values of k will give us a lot of equations. But it is going to be difficult to manipulate all those equations to prove that A0, A1 and all are 0. It will take a lot of effort to try to prove it just by the definition. Are you getting what I'm saying right now?
Yes.
Like if I just work with the conditions of being k balanced, it is going to be difficult to show that all the coefficients are 0. So what I will do now is write this as a polynomial f of x, and I need to prove that all the coefficients of this polynomial are 0, right? So what is a way to prove that the coefficients of a polynomial are 0? There is a way to prove that all the coefficients of a polynomial are 0, or there is a condition under which this happens. the condition under which all coefficients are 0 is basically the polynomial is identically 0, right? It's a 0 polynomial. Do you understand what I'm saying? F of x is identically 0, right?
Yes.
But how can we say that a polynomial is identically 0? Suppose you have a quadratic. When can you say that the quadratic is identically 0?
When it has more than two solutions.
Correct. More than 2 roots, right?
Yes.
So here, my polynomial has degree 49. If I can show that it has 50 different roots, if I can show that it has 50 different roots, then I will be able to say that f of x is identically 0, no? Correct?
Yes.
And then if it is identically 0, then each of the coefficients will become equal to 0, right?
Yes.
So basically, now we have converted the problem from a sequence and series problem to a polynomial question. And now we will try to think of it in that sense. F of x is a0 plus a1x plus a2x square till a49 x power 49. We are given that, or we are trying to prove that f of x has 50 different complex roots. The roots may not be real, it could be real or complex. But if we can show that it has 50 different roots, we'll be able to prove what we need to prove. However, now we have to think of the condition given in the problem. For k belonging to the set 3, 5, 7, 11, 13, and 17, the sequence A0, A1 till A49 was k balanced. That was given to us, right? So how do we use this condition? What is the meaning of k balanced? We know that A0 plus AK plus A2k is equal to A1 plus AK plus 1 plus A2k plus 1 and so on till AK minus 1 plus A2k minus 1 and so on. This is the meaning of k balanced. And it is k balanced for all the values 3, 5, 7, 11, 13, 17. So here, can we think of a way to figure this out about the complex roots and stuff? How to do that?
I'm not sure, but if we put like x to the 3 equals 1,
Right?
but x is not 1, it's one of the other roots.
Correct, correct. The complex roots, right?
Yes.
So what I would say is you can think of let epsilon be the kth root of 1. You are on the right track. Kth root of 1, but we are talking about the complex roots. Okay. So you should know from basic complex numbers, if you have x power k is equal to 1, what is the kth root? We can write this like this. X power k is e power I 2 m pi. And this is Euler's form of 1. And we can get x is equal to e power I 2 m pi by k, where m goes from 1 to k minus 1, right? X is equal to e power I 2 m pi by k is a complex root for the equation x power k is equal to 1, right? Do you know this complex number formulation?
Yes.
Basically, cube roots of unity and all, you know how to find, no?
Yes.
So what I'm saying here is, let's say this E epsilon is the kth root of 1, right? Then what we can say is epsilon can be written as e power 2 pi I m by k, where 1 is less than m is less than k minus 1. And here k could be anything from 3, 5, 7, 11, 13, and 17. Right? In that case, we have a property that when two numbers m and n are congruent to each other, modulo k, then epsilon power m will be equal to epsilon power n. For example, if you take a cube root of unity, you know that cube root of unity is one of them is this, right? E power I 2 pi by 3, right? Do you know that this is a cube root of 1?
Yes.
So you should also know that W power 1 will be equal to W power 4 because 1 and 4 are congruent to each other modulo k. W power 1 is equal to W power 4, W power 2 is equal to W power 5, because you can always take W cube common here, right? And W cube is 1. Do you understand what I'm saying?
Yes.
Whenever m and n are congruent to each other modulo k, e power m is equal to e power n. You can prove this for any complex roots. So for example, even if k was 5, and epsilon was e power I 2 pi by 5, you can prove that epsilon power 2 will be equal to epsilon power 7 because 2 and 7 are congruent to each other modulo 5, right?
Yes.
Okay, so now we will see what is the advantage of that. So remember our polynomial f of x was a0 plus a1x plus a2x square and so on till a49 x power 49. This was our polynomial. Now, if I have taken x as e power I 2 pi m by k, where m is going from 1 to k minus 1. What I mean by this is not x, I have taken epsilon as my epsilon is kth root of 1, right? It's a kth root of 1. And now what I will do is I will try to calculate what is f of epsilon. And f of epsilon would be a0 plus a1 epsilon plus a2 epsilon square and so on till a49 epsilon power 49. But now I can group these together and I will only take a0 plus ak, which would have been epsilon power k, by the way, plus a2k, which is epsilon power 2k. I will group these terms together, plus I will group a1 plus ak plus 1 epsilon power k plus 1 and a2k plus 1 epsilon power 2k plus 1, these terms together. And similarly till ak minus 1 plus a2k minus 1, and these terms have e power k minus 1 as common factor. What I mean to say here is you should realize that these terms all of these are equal. E power 2k is equal to 1, e power k is equal to 1, and so on, right?
Yes.
Basically, I can take this as a common factor outside, and this is just 1 everywhere. Here also, I made a mistake. I should have written E here, epsilon here, because that is A1 into E, that is the term. The next term I group it with is e power k plus 1. You should realize that e power k is equal to 1 by our definition. So this is also E only, right? And this is also E, right? Do you understand? I'm grouping the k terms apart. These are all k terms apart coefficients, right?
Yes.
So what I will get is something like this. F of epsilon is equal to A0 plus AK plus A2K, so on, plus A1 plus AK plus 1 plus A2K plus 1, all of which is multiplied by epsilon, plus A2 plus AK plus 2, and so on, epsilon square. And I can group all the terms like this, AK minus 1, A2K minus 1, and so on. And this is epsilon power K minus 1, right? Do you understand what I have done so far?
Yes.
I took my initial polynomial f of x and I have put x is equal to epsilon, where epsilon was e power I 2k pi by m. This is the kth root of 1, complex root of 1, right? And because e power m is equal to e power n, as long as m is congruent to n modulo k, therefore I'm able to group them together like this, right? Is it clear right now what I have said so far?
Yes.
Okay. So now the problem itself gives you what? The problem says that the sequence was k balanced. Sequence was k balanced, which means that actually this summation is equal to this, right? And is equal to this, right? All
Yes.
of these brackets were equal to each other according to the problem, right?
Yes.
So the f of epsilon is becoming what? You can take all of these as common factors and you can write it as A0 plus AK plus A2K and so on. And you are getting 1 plus epsilon squared till epsilon power k minus 1, right?
Yes.
And according to a property of these complex roots, because this is a kth root of 1, we have epsilon power k is equal to 1. And if you factorize epsilon power k minus 1 is 0, you will be able to prove that if this is a complex root not equal to 1, then 1 plus epsilon squared till epsilon power k minus 1 is always 0. Why? Because epsilon power k is 1. So epsilon power k minus 1 you can factorize, no, like this, e minus 1 and 1 plus epsilon squared till epsilon power k minus 1, right? Correct?
Yes.
And since we are saying that this epsilon is a complex root, it's not actually equal to 1. So this cannot be 0. So this must be 0 then, right?
Yes.
This is similar to the way you prove that 1 plus omega square is 0 if omega is a cube root of 1. Do you know that? Have you seen that before?
Yes.
Okay, so if omega is a cube root of 1, the sum of powers till omega square adds up to 0. If it was a fifth root of 1, you could have said 1 plus epsilon square plus epsilon cube plus epsilon 4 is equal to 0. So right now what we are saying is, since we took epsilon as the kth root of 1, this factor is automatically 0, no? This 1 plus epsilon till epsilon power k minus 1, right?
Yes.
So what that means is that f of epsilon becomes 0, right? Correct?
Yes.
So what we have proved right now is if you take the polynomial f of x is equal to 0, this equation, when I put x is equal to epsilon, I am getting f of epsilon is 0 if and only if the sequence was k balanced. Because only when it was k balanced, we were able to take the common factor, right? Otherwise, you would not have been able to take it common, right?
Yes.
Do you understand what I'm saying? Only because of the common factor, we were able to get this, right? Now, here, epsilon was what? Kth root of 1, or basically it was e power I 2 pi m by k, and m was going from 1 to k minus 1. Now think about it, this situation is true for different k, right? It was not just k balanced for one particular value of k, it was true for k is equal to 3, k is equal to 5, 7, 17, 13, and 11, right? Correct?
Yes.
So notice that for k is equal to 3, you would have gotten two complex roots here, right?
Yes.
One of the roots would be 1. We cannot take that root. We have to take the complex roots only, right? And
Yes.
here you would get 4 roots, 4 complex roots other than 1, right?
Yes.
So similarly for different values of k, we are getting 2 plus 4 plus 6 plus 10 plus 12 plus 16 complex roots, right? And basically this adds up to 6 plus 6, 12 plus 10, 22, 34, 16. This adds up to 50 roots. So what we have gotten is that f of x is equal to 0 if the sequence was k balanced for so many different prime number values of k. We have gotten 50 different complex roots for this polynomial, right?
Yes.
And because there are 50 roots now, the polynomial must be identically 0. And therefore, the question is done because now we know that all the coefficients must be equal to 0. Correct?
Yes.
I hope you understood it. This was a difficult problem because it involved a totally unrelated concept of polynomials and complex roots and stuff. But it's a nice problem, and such questions have been asked in Olympiads before. So I wanted to show you this one. I hope you've understood what we did. You can try out this problem for later. Let k, write this down. Let k belongs to natural numbers and k is congruent to 3 mod 4. S of n is equal to nc0 minus nc2k plus nc4k square and so on minus nc6k cube and so on. For any n belonging to natural numbers, you have to prove that 2 power n minus 1 divides S of n. So you can try this problem at home. I would say that this problem also will involve complex numbers. So that is your hint. Because if you want to simplify this binomial series, you might want to think about putting some complex numbers in order to get this S of n. So
What
that
does the on the top left mean of
uh,
the C?
which one? Which n? This n.
No, above and left of the C is 0, C2, C4.
These are NC0, combinatorial coefficient. No, this is n factorial by n factorial and 0 factorial. You don't know
Ah,
about
yes,
NC1,
yes.
NC2, right?
Okay,
You understand now, right?
yes,
That the coefficients that come in binomial theorem, right?
yes.
So in order to express S of n in a nice way, you might need complex numbers. That is your hint. And try out this problem. If you get the solution, do send it to me. You can reach out to me before the class, before the next session. But hopefully you've learned something from today's class. The questions were not super easy, but there were some questions that you would definitely encounter in Olympiads. So that's all from my side for today. I will talk to you guys next class. Okay. That's it from my end. Okay. If you have anything else, we'll discuss in the next class, or you can reach out to me on my WhatsApp. Okay.
Okay.
Okay. Thank you. Bye.
Bye.